All the controllers, the classical controllers which you have discussed, they are reactive controllers. What is reactive controllers? Certain things happens and then they take action. The output is not equal to input, so then the measurement, then the error comes, then they take the action, reactive, right? Predictive controllers are not reactive controllers. They predict certain things which is going to happen, so before it happens, they take the action. That is the beauty. Understand the concept of reactive controllers and the predictive controllers? What you do in control theory? You have got the reference, then you measure the output. If the output is less than the reference, then the error is there. It is going to the controller and the controller is giving the output. So that means the output has to deviate from the reference before the controller takes over, right? Predictive controller will not do like this. Predictive controller will based on a prediction. I will give one example of the predictive controller. Very typical example in my own house. We have got 4 brothers. When I was reading in one of the engineering college, oldest engineering college in Odisha. My brother was reading, studying in Odisha University of Agriculture and Technology in Bhubaneswar. I was in Burla. Then another brother was reading in Bhubaneswar in other college. Now see how it happens, how the predictive control works. In our village, we have got cow. During that time, cows are there, so they give the milk. Normally, we don't sell the milk, but the milk is being used for different purpose. Suppose there is a puja vacation. See the point, how the prediction comes in the picture. The puja vacation comes. So puja vacation suppose starts from tomorrow. So my mother will know that, okay, the vacation starts from this Friday. So my children will come either on the Friday evening or Saturday morning, right? So what she will do, knowing that we will come on Saturday morning, the milk which is there, which should have gone to other way, she will keep the milk. You see the predictive control. Predictive control, knowing that something is going to happen, not that we go there and we ask for milk, then she will keep it. No. That is the reactive controller. This is a predictive controller. They predict that this thing is going to happen and accordingly you take the action. Okay. And most of the classical controllers, even the state feedback controller, they are all reactive controllers, right? The minimum variance controller which we studied now, which is minimizing the variance of the output, is essentially a k-step ahead predictive controller. Because you are predicting what is yt plus k, okay? Then you found out what is the noise component, the predicted noise component, then this is the predictive controller, first predictive controller. Any predictive controller, how to predict? How to predict? In normal situation, we predict because of our intelligence. We know, we have got some information, so we predict that these things may happen, right? So for a predictive controller, usually it is associated with the model predictive controller. We use a model not for analysis, not for design of the controller, but for prediction purpose. This is name is model predictive controller, but actually it is used for predicting the output. Controller comes later on. The model is used for prediction. So in the model predictive controller, you take a model which will predict, right? Based on the prediction, you design the controller. Got my point? Nowadays you will find in the literature, people use the term model-free predictive controller. Model-free predictive controller. If you really look into that, I'll tell you, there is nothing like model-free predictive controller. There is nothing like model-free predictive controller. When they say it is model-free predictive controller, so what essentially they do, they collect the data, do the online estimation that the estimator there, that the estimator is predicting the output. There is no explicit model. There is no explicit model for that, but they estimate it, right? So there is nothing like a model-free predictive controller. You have to do something how to predict it, right? So traditional controllers are reactive. Many systems require anticipation of future behavior. Predictive control uses a model to forecast the system output, right? Can handle constraints or input output naturally. Okay, let's see. This example, I got it from some book actually, but it's a standard thing. This example I've taken from book. This is not my example. Suppose you are going to cross the road, right? Crossing the road, actually this is, Indian people can understand it in much better way than the foreign people. Once I was in Hyderabad in one conference. Two of my PhD students, they are from Palestine actually. Ihad Akila and his sister Lama, I think Lama is. So they came with me. I told her, I am going and you come, I will show you Hyderabad also. I have got some students working there. So I will tell her, I will organize the, car and other things, you don't worry for that. Those things taken care of. He told, okay, we will go. So what happens, the conference was in Osmania University. So we are staying in the town. The boss will come to take us to the conference site in the other side of the road. And we are on this side. Boss timing is there. So I will tell, okay, Yad, let's cross. Then Lama will tell, Dr. Swai, how we can cross? There are so many vehicles coming. I tell you come with me. You hold the hand of Yad, I am holding the hand of you hold the hand of Ihad, I am holding Ihad's hand. You come. Then we cross. Right? We know, I know because I am from India, so I know how to cross the road. Then Ihad told, I'm a bit surprised. There are so many vehicles coming from all directions. There is no accident, and people are crossing. I don't, this is the beauty of India. Here, this is the real independence. Humans, dogs, pigs, anybody can cross. Everybody can use the road. No problem. It is not other countries, right? So this example, actually that is only valid for Indian scenario. That is not valid for foreign scenario. Because foreign one you want to cross means you just see the light and you cross it. Otherwise, if you indicate that you want to cross, even if there is no crossing point, the vehicle will stop. That is the usual courtesy. Vehicle will stop and they will say, okay, you go. Very standard thing. Very standard practice. Vehicle will usually stop. Okay. So, but let us say this is an Indian system. So when you cross the road, you see here, I will go to the other side. So first what I will do, I will take a step, I look. See the point, this is the prediction horizon. I will look whether some vehicle is coming or not. To both sides, I look it, right? I look to both sides. And I will estimate on my own mind, which the model will do here now. On my own mind, the speed at which the vehicle is coming, whether it will hit me or not. So based on that, I took a step. Not only that I took a step, if while taking the step, I suspect that some vehicle is coming very fast, it can hit me, I will retract. This is what we do it, right? We always look to this side, right? In foreign countries, doesn't like work like this. When you are driving, I will tell you, suppose there is a roundabout. I have seen many roundabout here. You don't see anywhere. You just see to the right. Vehicle is coming, you stop. Because that's the right of the way, almost all countries, right of the way. You just see the right side. You see all the people, when we are driving, we'll just look like this. No vehicle cross. I'm not looking whether the vehicle is coming this side, that side. No. Right of the way. Okay. So it is different than India. So this is the typical Indian model predictive controller is being extensively used by the Indians in their day-to-day life. So Indians can use the model predictive control. They use it in daily life. For them, it is a play of a child. So just see what I'm writing here. You don't just look at where you are, you predict. See, remember here, you predict based on your intelligence, right? Now, what we will do here, we predict using what? A model. That's the only difference, nothing else. Okay. You assess not only current car positions, but also future positions. You start crossing only if the prediction shows no danger over the next few seconds. While crossing, you keep on looking, whether checking and revise your decision. This is the point. Key component is prediction, then optimization, then feedback. Depending on the situation, you do it. Advanced control strategy using system model to predict future behavior. Okay. Optimizes control inputs over the prediction horizon. I'll tell you later on this one, a little bit tricky thing here. Applies the fast control input. Okay. The core concept is you should have a system model. You should know prediction horizon until what time you will predict. Prediction horizon, cost function, and some constraints. Right. These are 3 steps. Predict future outputs using the system model. So model-free predictive control is a myth. It is not true. Actually, if you see it, they use one identification or estimation or something, a neural network or something, they will predict it. Solve an optimization problem to compute the optimal control inputs. They solve one optimal control problem. Apply only the fast control input. I will discuss these things. Repeat the process at the next sampling instant. Therefore, this MPC is very computationally expensive. MPC is very computationally expensive because each time step you predict, you solve the optimization problem, okay? You apply the controller and then predict next sampling instant. So therefore, when Manfred Morari did it, he did it for the process control systems, which is inherently slow. Because it takes time to do it. You are predicting, then you are solving an optimizer, right? It takes time, right? You can do it in microsecond. You can do it in milliseconds. It takes time, actually. So therefore, it is designed essentially for the process control plant. But nowadays, everybody is using the MPC, and the MATLAB. I don't know whether thanks to MATLAB or not. So MATLAB has got the MPC toolbox now. MATLAB has got all the toolboxes. Deep learning, reinforcement learning, all toolboxes. When I give the problem to the students, they will say, we have done the deep learning network. I told, deep learning network? Why? How could you do it? Professor Swai, we have got the toolbox. I looked to him. Yeah. Then I asked my student who is working on reinforcement learning. I told, Gunman, are you using a deep learning toolbox? Yes, Dr. Swai, I am using that. I thought I was thinking that you are writing your own code. No code. All are using toolbox. Everybody is using toolbox. Yeah. Everybody is using toolbox. Hyperparameter selection. The term people use, you will surprise. Hyperparameter selection of the optimization algorithms. Why you tell the parameter selection, why the hyperparameters? Where this hyper came? Huh? People, terms are used, that's fine. So you know why MPC shouldn't be used? Because very computational, very expensive, right? Receding horizon strategy, this is the point. David Clark used it initially in 1987 Automatica paper with one of the students. He used it. Manfred Murari, MPC came later on. First came GPC. I'm telling the history. Carl Ostrom, minimum variance controller. Peter Gotthard, David Clark, generalized minimum variance controller, followed by Peter Wallstead, we missed. Then David Clark, 1987 Automatica paper, 2 papers came. Generalized predictive controllers. 1990 Manfred Murari did it, Switzerland, MPC. And in between some variations came model algorithmic control, dynamic matrix control, in all the process control people. Because it is computationally expensive. Got my point? It is computationally very expensive. Even David Clark did not work with the GPC later on. Steve always says why David is doing all these things. He comes to our university doing the master's examination. I've seen him a couple of times. So 87 David Clark and 1990 Manfred Murari did this MPC controller which people are using now, right? Now one of the reasons because you are academics I'm telling you, and when this Manfred Murari is doing this MPC, one group is working on that in Europe. There is another group, adaptive control, came up. Adaptive control, this is, you see, MPC connect with the estimator, it becomes all adaptive, nothing else. Any controller, just adaptive. Recursive least square estimator, it becomes adaptive, straightforward. Some people said these are all useless, they are mad people. Why to do the adaptive? Make it robust. Robust controller, parallel development, robust controller, asymmetry and robust controller. Okay, robust controller developed. 1990, robust controller developed. 2012, I was in Denmark in a robust control conference. Then there is a person, a keynote speaker was there. This keynote speaker is from USA, some Bala. His student is Carl Stoll, my colleague in the mechanical department. He was doing PhD with him. It's Carl's supervisor. He was there. All the people who came there, they said that robust control became very popular amongst the people. You know what is the reason? The reason is system identification toolbox, it came later on. Robust control found is 1990. I think within 1 or 2 years, MATLAB released the robust control toolbox. Mu synthesis, yes, controller, robust control toolbox is available to the people. MATLAB released. MATLAB did not release other toolboxes. And got a lot of money, right? So therefore, robust control becomes very popular. Robust control. We are not discussing robust control here, except the sliding mode control we will discuss. So you see, unless you know the history, you cannot appreciate how the things are happening. Okay. Adaptive self-learning controller, 1980s, 85, 90s. You will find hundreds and thousands of papers of self-tuning control, adaptive control, self-tuning control, adaptive control, which you are going to do today in assignment. Okay, take a system, put these things, RLS, recursive least square estimator, do it. Many power systems, OP Malik is in Calgary University. I think he has published, I think, not less than around 20, 30 papers, a power system guy. So many papers, adaptive control. So that stopped, right? So the people work on adaptive control, that's fine. There is a guy in Automatica paper, came, it's an interesting paper. Tomorrow I will discuss while talking about nonlinear systems. Linear systems, linear time invariant system, when controlled by an linear adaptive controller, understand this point, linear time invariant system controlled by a linear adaptive controller becomes a nonlinear time varying system. This is the proof in 1986 Automatica paper. What a point. I think Bitmead is the author, remember. So, you see what happens normally when you do research, we always want to see that, let us say what is the formula is there, write a program, get some results and publish it. But the real thing, where it is coming, exact point, it's very difficult. People will say, why you will study nonlinear systems? We are working on linear systems. No, it's not the case. Linear systems controlled by a linear adaptive controller becomes a nonlinear time varying system. 1986 Automatica paper proved. Clear proof. One day, a seminar talk with Neil Monroe. He has done lots of work in Nyquist stability criteria and all these things. UMIST, he was there earlier UMIST, University of Manchester Institute of Technology. One day he was delivering seminar when I was there in Sheffield. Now you will surprise, I also don't remember that. The minimum variance controller, I told you, Carl Ostrom, David Clark, there's a Peter Wolstead who was in UMIST, was the colleague of Neil Monroe. Then Neil was explaining some theorem proposed by Peter Wolstead. Then he is telling, there are a couple of other people there, he told Peter did such a great job by deriving this theorem, and nobody remembers that, because people don't remember that. People will go to the algorithm and see it, because the theorem is important. Peter Wolstead, I remember, Neil Monroe told that Steve Banks, he was the editor of International Mathematical Control Theory. He was the head of the department at that time. He told, he's a Steve Banks. He told Steve, you also do not know. Peter did such a good job. You do not know. Only small theorem. See, we always forget those things, right? So similarly, you see where it come from, you must know these things. Otherwise, doing these things has no meaning, right? Let's go. Receding horizon control. This receding principle first used by the David Clark, later on by Manfred Murari. Continuously, receding horizon means you see it and you continuously look at, and as you go forward, you see further. Now you see until this point, if I go there, I will look a little bit further, then take my decision. I should go there, then I will look a little bit further. So that's the point. Unlike PID, MPC explicitly considers future system behavior. Control actions are chosen to optimize performance index. Model-based decision making. Important point is, I am telling you just an important point, the model which you are using, this is the important point. The model which you are using in the model predictive control not necessarily should be perfect. It is not system identification. Even if there is some model imperfections, still we can manage it. Still we can manage. That is the key point. Model may not be perfect, but you require at least a fast-hand model to do this. Just only simple mathematics. State feedback controller, linear quadratic regulator, linear quadratic Gaussian controllers, even robust controllers. All these controllers in most of the cases, they cannot eliminate steady state error, which is a very important component. Got my point? Steady state error can be eliminated provided the system has its own integrating action, or you design an integrator. It is the integrator who has the capability to eliminate steady state error. Nobody else can do it. Optimal controller cannot reduce the steady state error to 0. No. You solve the matrix Riccati equations, okay? It cannot eliminate, right? An integrator must be there in the system to eliminate the steady state error, right? In most of the cases. Why most of the cases? I can take 100% cases, right? So this formulation, what happens? One integrator is intentionally built into the model. System model is xm k plus 1, x dot is equal to ax plus bu. X dot is equal to ax plus bu. In our discrete domain is k plus 1 is equal to axk plus b uk, right? What they do? They integrate one integrator, okay? By integrating one integrator, what is done? They define a new state variable delta xm is equal to xmk minus xmk minus 1. The essentially integrator is, then they get this model. This is not the actual model of the system. This is the model of the system with an integrator. Why integrator? Because eliminate the steady state error. MPC cannot eliminate the steady state error, right? So put an integrator at the beginning, right? That this model is being used now. Now our model is here. This is the model. This is the model. This is not the model of the system. This is the model of the system with an integrator. I am again repeating the point. This is the model of the system with an integrator, right? If you are not obliged to use integrator, if you are not using integrator, you can simply use that model. That is not a problem. It is not a problem, but at the end you have to use an integrator. Okay. So this is the model. Xk plus 1 is equal to axk plus b delta uk. Where delta uk is equal to uk minus 1. This model is being used to predict the output over prediction horizon. Okay. What is yk plus 1? What is yk plus 2? What is yk plus 3? What is yk plus something, right? You predict based on this model. I am not deriving those things. Now if you predict it, you will find this prediction model will be like this. This y is equal to capital Y is the predicted value of the output, yk plus 1, yk plus 2, yk plus np, prediction horizon, up to what step you are predicting. This capital Y here, you see, this capital Y is the prediction equation, prediction, right? Yk plus 1, yk plus 2, yk plus 3. It is possible to do. So if you do it, this is the equation. This is the predicted model or prediction output. F is equal to Ca, Ca square, Cnp, and phi is this matrix. Very easy to algebraically you can find out. Once you get this prediction, then you minimize a cost function. Remember this capital Y is a predicted output over a particular horizon. Again repeating this point. Y is equal to, I am writing again here. Y is equal to y k plus 1 given ki, y k plus 2 given ki instant, y k plus 3 given ki, similarly y k plus np. Okay. So these are all predicted output. Okay. And what you do, this You see NP times, this is the reference signal. So that is a performance index. First you predict, then you optimize. Which one? This performance index. Reference minus the output into some weight and the control input, delta U, these things, just like here. J is equal to, I am writing a small way, R minus Y transpose R minus Y plus delta U transpose into delta U in general. Just a minute, I am just modifying these things here. In optimal control, we optimize J is equal to X transpose QX plus U transpose RU. LQR optimization. LQR optimization. Here, you are also doing optimization. What you do? Your performance index is R minus Y transpose into R minus Y plus delta U transpose delta U, right? And you are just putting another weight just to control. So that is the performance index is J is equal to, I am writing here, R minus Y transpose WY R minus Y plus delta U transpose W U delta U. This is the performance index. X transpose QX, U transpose RU, same thing. So first you predict by using a model, first you predict, then you optimize this performance index, right? Now it will give you, these are the weights, control weights. Now it will give you a control law, this is the control law. This is the control law. What I want to say, if you are using a model to predict the system, then you can use that particular performance index and get a clear-cut mathematical expression, just like phi transpose WY phi plus WU inverse phi transpose WY, these things, right? If a model-free predictive control, what they say, actual which is not, there the optimization is carried out in a different way. You cannot get a clear-cut expression like this. Because there is no model, you are estimating the model from the data, right? But essentially, you will not get this thing. That is the only difference. Suppose you are using a neural network to predict those Y, right? So therefore, you will not get any expression, a closed form expressions like this, right? Otherwise, there is no difference. So you get delta U. Then after getting delta U itself also has a control horizon. Delta U k plus 1, delta U k plus 2, delta U k plus 3. And you use the first one. Now the question is, are you a fool? If I am using only the first control input, then why should I compute the control input over a horizon? You understand the question first? He is telling that delta U is this. Note that the optimal control vector delta U contains here. Delta U ki plus 1, delta U ki plus 2, delta U ki plus nc minus 1, right? And you use only this one. The next step, right? Get the model, predict the output over a particular horizon, that is y k plus 1, k plus 2, k plus 3, right? Optimize that particular thing, you will get the control action. This control input has also its own horizon. And you use only the first control input in the next sampling instant, because it is online. This is online. Now the question is, we usually ask the questions to students. MPC will give you a sequence of control actions. over k plus 1, k plus 2, k plus 3, and we will ask you, use only the first one. That means it's just like this. You are going to have a lunch, so there are dishes. I will tell that in the dish, this is what, this is one dish, this is another dish, this is another dish, this is another dish, but you only take only first dish. No, then you will say, what the hell you are talking? You are giving me 10 dishes, and you are asking me that you only eat the first dish. Then why the hell you gave this 10 dish? You understand this point? It sounds ridiculous, yes or no? See the delta uk plus 1, delta uk plus 2, following the receding control principle, implement the first sample. Then if you want to implement the first sample, why to compute all these things? Now the question is something different. This can only be understood from the chess player. You see the chess player, what they do you know? When the person is playing chess, world champion, they know if I apply this control input, what are the possibilities that that fellow will do? If I apply this one, what are the possibility? If I apply this one, what is the possibility? If I apply this one, what is the possibility? You got my point? He has got 10 things in mind, but he will use only one. And then after that, depending on his action, then he will think. Got my point? The same thing is being, it's not myopic. We don't say MPC is not myopic. MPC sees many things, but do only one. But he has got a knowledge. He has got a knowledge that these control actions, right there. Got my point? So you have got the model, you have got the optimizer, then you implement these things. Each sampling instant. Because you are doing it at each sampling instant, so therefore it is computationally very expensive. The system is very fast. It is always advisable that don't use MPC. Got a point? But if you want to publish papers, that's fine. I have nothing to say. We are doing it, you have to do it. Got a point? MPC should not be used in that place. Okay?
How do we select that right and read?
Prediction horizon and the control horizon, NPNC. 1987, when David Clark did it, NPNC, because I was there in 1994. So, there are many people work. I'll discuss something. That what is the effect of the prediction horizon on the performance of the controller? What is the effect of the control horizon on the controller? To be very frank, I'll tell you, its effect is not that much significant if you have got a little bit of knowledge about the system physics which you are controlling. The NP should be 10, 20, you should find. Actually, theory is the settling time is there. You should, suppose your sampling time is 1 second and settling time is 20 seconds. So you take NP at least 20. Okay. Suppose you are sampling at 0.1 second, settling time is 5, so you take NP as 50. Just settling time, NP. And NC, less than NP, 5, 10 will do. So it is not very significant. We do not see any significance. That's my experience I'm telling. Okay? So nowadays nobody is doing, not only this NP and C, choice of sampling time. Choice of sampling time in system identification, in adaptive control, it is a major research area earlier days. Nowadays, sampling time you can select. So NP should be almost cover the settling time of the system. Okay. Settling time of the system. And 10, 20 should be fine. Only problem is it's computationally very expensive, very expensive. And I think today tutorial, I don't know, Professor Amal, did I give MPC is there in the today's tutorial? So the MPC, I have got I have done it. Okay, one thing I'll do, because we're academics, I learned it during my time, I must share with you, which we'll do in the genetic algorithms also in this course. Practice active reading. What is active reading? I learned it from one of my friends from Singapore, Tiam Lin G. G will always come to my house and he will say, "Hey Swai, your wife can make roti paratha." I told, "What, G, you are telling roti paratha? Roti is something different, paratha is something different. What is roti paratha?" No, then when I went to Singapore, I found this roti, they said roti paratha. He will say, "You make roti paratha, I will take." Then G told me, active reading, I always do that. Suppose a recursive least square. There is no need of going much detail into the recursive least square. If you really need it later on, you just see the algorithm, write a simple code for a simple system and see how it is working and keep it as a file. Keep it as a file. Right? Active reading. Not that simple read, just read it. Say MPC, you know MPC, how this model is there. Then you see, this is how the optimizer. Just do it, simple thing, and see how it is working. Then only, if you need it, then you use it. I'll tell you, genetic algorithms, I have done it quite long back. Because the genetic algorithm toolbox was developed by Peter Fleming by MATLAB to genetic algorithm toolbox which you are using now. It was developed by Peter Fleming. Peter Fleming was the head of the department, Sheffield University, automotive control department. Okay. So all big sorts were there in control department, all big sorts. Huge big sorts are there. Peter Fleming was a HOD in that time. He has got 13, 14 students working on genetic algorithm, out of which Carlos was working on this multi-objective optimization problem. So, genetic algorithm, I learned it there. I have got active reading, I put it. So one day, I think 2011 or something, we have got a student from South Africa, Michael Neath. We are working on the wireless power transfer. I was looking to the control aspect, a modeling and control aspect. By the time one model we have published in transaction power electronics. Then Michael one day come to me. I told Michael, just like it came to my mind. I told Michael, you do one thing. Why don't we use a genetic algorithm, multi-objective optimization to optimize the parameters of the PID controllers for this wireless power transfer system? He told, I don't know genetic algorithm. Then I went to the computer, active reading. Genetic algorithm, simple code is there. Then I explained Michael. I told Michael, you come and I will explain you. That was around 3 o'clock. I told, okay, Michael told, I understood it. South African, white guy. After 2 weeks, I'm just going out of my office, just trying to go, right? Take the car and go. He knocked my door. I told Michael, what happened? No result. What result? What result? I'm asking like this, what result? None that multi-objective genetic algorithm. And also, yeah, I told you last week, yes. Do you have time? Just see, I'll show to Uday later on. Uday is the main supervisor. But you just see, you check it. You will surprise, I gave him a simple MATLAB code. Weeks before, he doesn't know about genetic algorithm, I explained him. He implemented in the software Experimentally he did it. He got the result. Make a draft of the paper. My paper is published in, we send it after 2 months, it got published in Transaction Power Electronics. Such type of people, I am surprised actually. Just active reading. So I will always advise you people, do the active reading. Not just read it. Write a small program, keep it in your place. If some students come later on, you do it. I have been doing it for a long time. I've got another student working on this capacity power transfer, William Su from Taiwan. Then he wrote a flow chart of a controller. I told William, this is a fuzzy problem. What the hell you are doing here? You are writing a flow chart. He told, fuzzy logic, I don't know anything. I told, come to my office. I'll tell you fuzzy logic, I'll give you the code. Then I gave code to William. Then he did it, same thing. We published 2 papers. One is transaction in industrial electronics and the other is IET power electronics. It is because it is possible, because the active reading, fuzzy controller is there, membership functions defined and how to generate fuzzification, defuzzifications, and you should understand that thing. Okay? Any questions here before we proceed? No. See here. Coming to that point. Yes, I'll explain you. You see here, XMK plus 1 is equal to AM XMK plus BM UAK. YK is equal to CM XMK, right? Now, suppose delta XM is equal to XMK minus XMK plus 1. Delta XMK. Then delta XM K plus 1 will be equal to XM K plus 1 minus XM K plus 2, like this, right? Delta XM K is equal to XM K minus XM, sorry, XM K minus 1, XM K minus 1. Delta XM K by definition is XM K minus XM K minus 1. So delta XM K plus 1 will be XM K minus 1 minute. Just give me time. Let me do it. This will be XM K plus 1 minus XM K. Do you understand this thing? If I am defining delta XM K is equal to XM K minus XM K minus 1, then XM K plus 1 in place of K plus 1 will be XM K plus 1 minus XM K, right? Now this one, if you do it, this will be AM XMK plus PM UK, right? Because by definition you see here XMK plus 1 is this one, right? Minus delta minus XMK. XMK is just minus XMK is AM XMK minus 1 plus BM UK minus 1. Now you subtract it together, then you substitute, you see this is XM AM XMK minus XMK minus 1. That is definition in delta XMK, so this model will come automatically. So that way, by integrating, they get it. This thing has been, this approach is used by Liu Ping Wang. She's in Monash University, or sorry, in Melbourne. She's in Melbourne actually, this lady, this Chinese lady. Any questions, other questions? Tomorrow we'll study, yes.
Sir, with respect to time horizon, what is the difference between MPC model predictive control and LQR, linear quadratic regulator?
Linear quadratic regulator, good question. Linear quadratic regulator is a reactive controller. It is not a predictive controller because it doesn't predict. It doesn't predict anything, and if certain things happens, and you take the actions. No. No, it's not a predictive controller. Okay, no, I'm explaining these things. I'm explaining these things. Your questions are very valid questions, no doubt about that. This is why. Now this is the controller. This is the system. So you get the system x1, x2, x3, right? Then you multiply by some gain k. You get multiply by gain k, and this one is going to here, and you apply it. It doesn't matter. Now here, system is there. It is producing the output. The state variable is there, x1t, x2t, x23. You measure it. Then you are not predicting. You are not using x1 t plus 1 or x2 t plus 1 or t plus 2. You are not doing that. You measure it and you compare with the reference and then apply it. So yes. No prediction is used. LQR, no prediction is used. Yes. If I do it, yes. It's not a predictive controller. You predict, and based on the prediction, you take the action. So therefore, it is a little bit powerful, similar to Kalman filter. We say why Kalman filter is very effective. You predict, okay? You predict that this fellow is going to do these things. Then you again take the measurements to check whether your prediction is correct or not. Then if you check it with your prediction, and if there is some error, you modify your prediction. So therefore it is powerful. And I will share with you, Kalman is the only person, Steve always tells, he's the only person who leads a life of a Hollywood film star. Because whenever he comes to deliver a lecture, people come during those times $2,000 US. And the audience is full. That fellow is from Hungary. His father migrated to USA. Ari Kalman. Very powerful Kalman filter. It is extensively used nowadays, Kalman filter. Any questions? No. Based on the present time, you predict, right? Yeah. You are at time k, okay? You are at this time. Now you predict. See, I'm just telling, I'm just moving now. So I am here. Now I predict 10 steps. Here, there, right? 10 seats, I will predict who will sit. Then I make one step. Once I move one step, then I will start predicting 10. So receding, you see, I will still predict there. Now similarly, if I take this step, again I will predict.
But control horizon is 5, right?
Yeah, control horizon 5.
But you are giving 5 inputs and you are predicting 10.
Yeah.
So for 5 it should be 5. For last 5 outputs.
No, it's not. It doesn't work like this. It doesn't work like this. your optimizer is there. There is an inherent optimizer in the MPC, which is optimizing a performance index. Okay? So that particular performance index is taking how many steps you are predicting, okay, and giving a control input. That optimizer can give you. Optimizer has nothing to do with how many control horizon is there. It doesn't bother with that. Okay, I mean, so you predict, okay, and depending on you see how many control inputs you want, you tell to the optimizer will do that thing. Not that optimizer will tell you are predicting 5 steps, why you are using 10-step prediction horizon. No. Optimizer will take 2 inputs separately. Got a point? 2 inputs separately it will take. It will not, your question is valid. You are saying that 5, then I will ask, why 5 input to control horizon, you are using only 1 input in the next step? No. You, just like the chess example I gave you, okay, although you use only 1 step control, but you think, if I would have used this control input, what would have happened? This control input, that's the point. It's a bit tricky things in the predictive control. And remember, for doing all these things, the prediction horizon and control horizon has no meaning. I mean, it is not that significant. You will find in many of the power system journals or any things, people get some results 97% accurate. Another will get 97.2%. Is it significant? You got a point? So NP and NC doesn't have significant, provided it is within the range. And your question previously that, because we are not discussing a constant one. Usually the input is constant, output is also constant. Right? So you have to constrain those things. If you are a layman and you do not have a constrained optimizer, you do one thing. You compute the control law just like this. Then you see, you compute the control law, then you say like this. Without an optimizer, if delta UK is greater than delta U maximum, delta UK is equal to delta U maximum. Just put it like that. That is a constant. But usually nowadays quadratic programming, there are so many other solvers are there. There are so many other solvers are there. One time, how much time is there? Time is gone? Time is gone. Then we'll see. Because I will tell you later on, most of the cases we are solving these equations. But in stability studies, if it is an inequality, do you understand this? You can solve what is X is equal to B, X is equal to A inverse B. That is easy. But find out X when X is less than B. Just a difficult problem. Inequality. Inequality does not have a unique solution. Linear matrix inequality is an inequality. Equality is easier to solve. Inequality is equal to 1,000 solutions. Okay? So in that case, whenever the inequality comes, especially Lyapunov stability criteria and many cases, inequality, then you have to find out of so many possible solutions, which is a feasible solution. LMI feasibility, they say it. Okay, you understand this problem very carefully actually. It's a equality, inequality, uniqueness, non-uniqueness. So those things are important. Solution is there, is available everywhere.